So now let's invite Dr. Chen to bring us an overview of OpenMMLab and its recent updates. I will first briefly introduce Kai. So Dr. Chen is currently a research scientist in Shanghai AI Laboratory, leading the OpenMMLab team. He received his PhD degree from the Chinese University of Hong Kong. He has published more than 20 papers on top-tier conferences and journals in computer vision, receiving more than 5,000 citations.
Okay. Hello, everyone. I'm Chen from Shanghai AI Lab and also the lead of OpenMMLab. Today, I will talk about OpenMMLab, a foundational platform for computer vision research and production. With the development of deep learning and computer vision, big companies and research institutes open source deep learning frameworks such as Caffe, TensorFlow, and PyTorch. Of course, today, PyTorch has almost dominated the AI research community. With these frameworks, the cost of conducting research and implementing algorithms greatly decreases. More researchers tend to release the code when paper is published. On top of PyTorch, we hope to push one step forward from a unified deep learning framework to a unified algorithm framework. So we announced the OpenMMLab project in 2018. OpenMMLab is an open source computer vision algorithm platform with a unified architecture for training and evaluation. It covers more than 30 research areas, implementing over 300 algorithms, including classic and state-of-the-art ones. We also released more than 2,000 pre-trained models and built fair benchmarks with standard training settings. We hope these models can provide a solid foundation to researchers. OpenMMLab was first released in 2018. At that time, there are only two packages, MMCV and MMDetection. In the next year, 4 new codebases were developed. In 2020, we supported more mainstream tasks, such as classification, segmentation, 3D object detection, etc. In the past 2 years, we kept open sourcing toolboxes for new areas and closely collaborate with colleges and research institutes to work on more directions. In the future, we will extend OpenMMLab and more new projects are coming. Today, we have built a powerful framework based on PyTorch. We developed 2 foundational libraries for computer vision, MMCV and MMEngine. MMCV implements lots of network operators that are missing in PyTorch. These operators are supported on both CPU and CUDA. It also implements common data augmentations and image processing functions. MMEngine provides a generic and universal training engine, serving as a foundation of all algorithm codebases. Based on MMCV and MMEngine, we construct codebases for different research areas, like classification for image classification, MMDetection, MMSegmentation for image perception, tracking and MMAction2 for video understanding, MMEditing for low-level vision. These codebases involve most mainstream research areas in computer vision. Towards industrial applications, we develop MMDeploy for model deployment. It bridges the gap from research to production. OpenMMLab has gained great community impact these years. It has received 70,000 stars on GitHub. It is noted that OpenMMLab is not a competitor of PyTorch. Instead, it is part of the PyTorch ecosystem. We just show this figure as a reference. More importantly, there are more than 1,000 contributors from over 40 countries. These contributors actively commit codes to OpenMMLab projects and make it stronger. In the academic community, OpenMMLab projects have been adopted by over 1,000 papers, including many high-impact ones, such as Wind Transformer. One of the advantages of OpenMMLab is that it provides high-quality implementations for different areas, making it a good benchmark for when researchers want to evaluate their models on downstream tasks. Meanwhile, we have seen more than 20 Chen winners adopting OpenMMLab as their codebase. Next, I will briefly introduce some codebases in OpenMMLab. The first one is MMDetection. It is perhaps one of the most well-known computer vision libraries. It supports instance-level recognition tasks such as object detection, instance segmentation, and panoptic segmentation. In later sessions, other speakers will talk more about it. Classification provides various backbones and pre-trained models for downstream tasks. It also studies how to train a better network with different policies. In classification, you can find most classic and trending networks and easily build your own. Segmentation is the most widely adopted semantic segmentation toolbox in recent years. It can be applied to general scene understanding, self-driving, remote sensing, and medical image analysis. It incorporates over 30 algorithms and releases more than 400 models with lots of application studies. We provide a standard benchmark with fair comparison. MMDetection 3D is a platform for general 3D perception. It supports 3D object detection methods with different sensors like cameras and LiDARs. Since it adopts a similar design to MMDetection, it is much easier to integrate 2D detectors and use modules from MMDetection. MMRotate extends MMDetection to implement rotated object detection, which are useful in remote sensing or text detection. MMOCR is a toolkit for text detection, text recognition, and the corresponding downstream tasks, including key information extraction. It supports a variety of state-of-the-art models and provides a comprehensive set of utilities which can help users assess the performance of models. MMPose is a toolbox for pose estimation. It supports 2D and 3D outputs, and also it accepts image or video as the input. And also it can have different representations such as mesh or key points to represent the pose. And also it supports the body, face, and head, hand, and also other different parts. MMation 2 implements various algorithms for video understanding tasks, including action recognition, action localization, spatial temporal action detection, and also skeleton-based action detection. We support over 20 different algorithms and 20 different datasets for these tasks. MMEditing is a image and video editing and generation toolbox. Supports popular and contemporary inpainting, matting, super resolution, frame interpolation, and generation tasks. And also it supports some very popular methods like diffusion models for text to image, and also some 3D aware generation. Besides developing toolboxes for research, we step one forward to production. From research to production, what we need to do is to deploy the model on specific devices, such as CPU, GPU, mobile phones. When we have developed a novel algorithm and obtained a PyTorch model after training, a general pipeline for model deployment is to first convert it to some intermediate representation, for example, Onyx, then convert it to the format allowed by the inference engine on the target device. During this process, we need to resolve issues such as how to convert the model, how to implement the operators that are not supported by the IR or the inference engine. Now we present the architecture of MMDeploy. MMDeploy naturally supports OpenMMLab projects like classification, detection, segmentation, etc. It mainly consists of 3 components: model converter, SDK, and backend extension operators. The model converter converts PyTorch models to IR models, and then IR models to inference engines. SDK provides simple and unified APIs to execute the model, and users can develop applications based on the SDK. We also implement lots of operators on different backends and devices. There are 4 major advantages of MMDeploy. Firstly, as an open framework, it supports various inference engines such as TensorRT, Onyx Runtime, and also OpenVINO, LibTouch, etc. And it is compatible with multiple platforms, including Linux, Windows, Android, and macOS. Besides, MMDeploy allows users to develop with different languages and can be flexibly integrated to the production system as required. For example, just use the IR model or inference engine models, or integrate the whole SDK. Here is an example of how to use MMDeploy to deploy RetinaNet to NVIDIA GPUs. The first step is to run a single deploy script to convert the PyTorch model to a TensorRT engine. Then we can obtain a result photo with the binary files and configs. Next, we can use the Python SDK or C++ SDK to run the optimized model on GPU and enjoy the acceleration. Okay, we have introduced lots of OpenMMLab projects and we say that it's fancy, wonderful, and perfect. But what is the benefit of adopting it? Since some researchers may write code just from scratch PyTorch without any algorithm code bases. So by adopting OpenMMLab, there are some significant advantages. The first one is unified architecture. Users can learn once and use everywhere. Since architecture and APIs are almost the same for all OpenMMLab code bases, you can also implement once and use anywhere. For example, implement a backbone in MM classification and use it for object detection, segmentation, post estimation with just modifying config files. The second one is unified benchmark. OpenMMLab provides fair baselines for academic research. For some research areas, different papers may adopt totally different settings, and we cannot conclude whether the model matters or the hyperparameters matter. In OpenMMLab projects, we investigate lots of training tricks and hyperparameters, and benchmark dozens of models under the same or similar settings. This benchmark makes it easier to compare your work with others. Then the modular design. OpenMMLab codebases are carefully designed based on research experience and engineering practices. Users only need to write a few modules instead of the whole pipeline, making it faster to develop and try new components. Lastly, we provide high-quality implementations. The efficiency and the performance are usually higher than other ones, and the strict code style make it easier to read and maintain the project. Okay, that's all. In next sessions, we will dive into more details of OpenMMLab projects. Thank you.